Hello, in this video I'm going to run through correlation and regression analysis in exactly the same way as I would like you to run your fear, anxiety and stress analysis for your write-up. In this example I'm going to use the weight loss data that we used in the workshop just to run through the process and procedure of what I'd like you to do. So the first thing we're going to do is to explore the data to see if the data are normal or otherwise. So to do this, we're going to analyse descriptive statistics, explore, and we transfer all three of our variables. In this example, I'm going to use exercise, food intake, and weight loss. They would originally have been in this side here, but I've done this analysis previously, so they're already in the dependent list for me. By clicking on plots, I unclick stem and leaf, click on histogram, and then normality plots with tests, because that will give me the Kolmogorov-Smirnov output. So click on continue and OK, and we'll just wait for the output to arrive. Okay, so here we can have here we see the case processing summary, the number of participants, no missing cases. We'll just skim past the mean and come straight to the Kolmogorov-Smirnov table. As you can see, the sig or p values are all greater than 0.05, so this tells me that the data are normally distributed. And just to confirm that, I'll just scroll down to the frequency histograms. You can see exercise looks pretty normal. We've no outliers. And food intake again looks quite normal. It does look a bit skewed actually, but the Kolmogorov-Smirnov table tells me it's normal, so I shall move on to the box plot. Again, we've no outliers in food intake, and here we have the weight loss data, which again is deemed to be normally distributed, so we're okay with that. And we'll just check for some outliers, and we don't have any outliers there. If you do find that your data do violate the normality assumption, then you can report that in your report, but I do want you to proceed with the regression, because obviously the regression is a parametric test, but just make a note of that at the beginning of your results section, that the decision was taken to proceed with the regression, because this is an exercise in regression, so it's important to do that. So now we've completed our data screening for normality, we'll move into the first hypothesis. So similar to the hypothesis that you're exploring in your write-up, my hypothesis is that exercise, food intake and weight loss will be correlated. So let's have a look at this. We go into analyze, correlate, bivariate. So the variables of interest are exercise, food intake and weight loss. Move them over into the variable box, make sure Pearson's is ticked and click OK. So here we have our correlation matrix, and we can see that there are some significant results. We can see food intake is not significantly correlated with exercise. Weight loss is, and if we look at weight loss and food intake, we can see that significantly correlated with is significantly correlated as well, and it's negatively correlated. So what that tells us is the more food we eat, the less weight we will lose, because it's as one score increases, the other one decreases. With weight loss, this is a positive correlation, so the more exercise we take, the more weight we lose. So we can comment on that and say, yes, there were two significant correlations. However, it wasn't, the hypothesis couldn't be supported fully because one of those correlations was not significant, and that's exercise and food intake. However, we're still going to include both predictors in our regression, because remember, the next part of the analysis was to explore the data to see which is the strongest predictor of weight loss. Now, we kind of already know what it's going to be, because we can see food intake isn't correlated with weight loss, but we're going to do two separate regressions and see what the data tell us. So to do the regression, we're going to analyze regression linear. Our dependent variable is weight loss, because that's what we're trying to predict. And we're going to do a hierarchical regression where we enter the variables in one at a time in separate blocks. Every time we enter a variable into the regression, the variance associated with that variable is removed. So we can enter them one at a time and look at the change in the R-square value. Remember, the R-square is the proportion of variance explained by that predictor. So for the first analysis, I'm going to enter exercise first, click next, and then food intake second. I'm also going to ask SPSS to tell me the change in the R-square between block 1 and block 2, and then continue and OK. So the first thing we look at is the order in which we enter the variables: exercise first, food intake second, and then to the model summary table. What I'd like you to report is the R-square, which is the variance explained by both variables together. That's 63% of the variance, adjusted to 58%. Remember, the adjusted R-squared is a more conservative estimate of what the R-square value is. Now here we can see when exercise is entered first that it's a significant predictor, and when we enter food intake in the second block, we can see the change in the R-square value. And if we look at the R-square change here, it goes from 35.4% when exercise is entered on its own, and it actually increases by 27.6%. So these two added together give us our total 63% of variance explained. And SPSS is telling us that entering food intake into the regression is actually improving our ability to predict weight loss. If we look at the ANOVA table tells us that both our models are significant, so we would report those in the standard way that we report ANOVA. So F, then the degrees of freedom, which will be 1 and 17. We report the 1 and 17, the regression and the total degrees of freedom. Our F value, and then our P value, which is less than 0.05. The same for the second regression, the second block. Again, our F value, degrees of freedom, and our F value, and then our P value. So we then move on to the coefficients table, which tells us a little bit more about what's going on. What I would like you to do is to construct two regression equations. So for the first model, it would be y equals a, which is the intercept, which is this value here, the constant, sorry, 1260.67, plus b, which has a value of 13.48, which is our value for exercise, times by x. And because we're not solving the equation at the moment, I'd just like you to put x in brackets to complete the equation. So here we can see exercise is significant. And then if we move down to the second coefficient, again I would like you to construct a second regression equation. Again, y equals a, which this time is 1856.26, plus b for exercise, which is 7.62, plus b again for food intake, which is minus 1 0. Sorry, 1 1. So those are the two regression equations. Now, if we look at what's going on here between Model 1 and Model 2, we can see that when exercise is entered on its own into the regression, it is significant. However, when food intake is entered, food intake actually is a much stronger predictor, and therefore it renders exercise non-significant. And if we look at the standardized coefficients, we can see that looking at these standardized values, that food intake is a negative predictor, but it's also the only significant predictor. So the story is basically, depending on the order in which you enter the variables, the story can tell quite a different account. However, when we get to the coefficients table, we can see the true picture emerging, that food intake is the only significant predictor of weight loss, and it is a negative predictor. In other words, the more food you eat, the less weight you're going to lose, and that exercise is non-significant. Okay, so once you've done that, I would like you to run the process again, this time entering food intake first and exercise second. So I'm just going to run through this now. Analyze, regression, linear. I'm going to reset, and I'm going to put weight loss again back as the dependent variable. This time I'm going to enter exercise in the first block. Sorry, food intake in the first block. Click next, and then exercise in block 2. Again, remembering to click the R squared change, because when you reset SPSS, it forgets all these items that you've checked previously. I'm going to click on OK, and then I'm going to look at the output. Again, we can see the order in which we entered the variables: food intake first, exercise second. Looking at the model summary table, we can see that both variables together, as before, are explaining 63% of the variance in weight loss, adjusted to 58%. However, something slightly different is happening here, and we could have kind of predicted that from our previous analysis. However, I really want you to do both, because it's a good exercise in looking at data and getting a feel for the data. So we can see when food intake is entered in block 1, it's a significant predictor. However, when we enter exercise in block 2 and we look at the R squared change, it's only increasing the model by 9%. And this increase is not significant. So entering the variables in this way is actually giving us a more realistic account of what's going on with the data. When we look at the ANOVA table, again we can see that both models are significant, because ANOVA is telling us that with both variables entered into the regression that they are explaining a significant amount of variance. However, it's only when we come to the coefficients table that again we can see this true picture emerging. So when food intake is entered first, again, as we know, it's a significant predictor. However, when we enter exercise into the regression, the variance associated with food intake reduces slightly. This is possibly because although the correlation between food intake and exercise wasn't significant, they were sharing some of the variance explained in weight loss. So this will account for the slight reduction in on these standardized coefficients. Remember, these are the ones that we can use, these are the data we can use to tell us about the relative importance of predictors. So we can see that when exercise is entered into the regression, again it's a non-significant predictor. So the coefficients table is crucial in interpreting your regression. Again, I would like you to construct two regression equations. So y equals a, which is the constant for model 1, plus b, which is the coefficient associated with food intake times x. And then a second regression equation, which is y equals a plus b, which is b1, which is food intake, and b2, which is exercise. So I hope that's been of some help, just quickly running through how I would like you to run the analysis for your results section. Thank you.